Hello, I'm Gio. This is my IDSB on Artificial Intelligence in Music. I started this year with the idea to make a vocal synthesizer for this IDS. This was motivated by the fact that I was enjoying producing music, and since I couldn't sing myself, I thought it'd be pretty cool if I could make a machine sing for me. But first things first, in order to make my own vocal synthesizer, I needed to understand how to actually use one, as well as how it really works inside. There are many excellent Japanese vocal synthesizers, and I found a few covers of songs that absolutely blew my mind on how human they sounded. So, I spent the first month of the school year playing around with different vocal synthesizers and trying to incorporate them into my own songs. I initially chose Utao as the vocal synthesizer to experiment with, since it is free and quite popular, so there were many tutorials on how to use it online. As a first experiment, I made a short instrumental and used Utao to make a vocal top line to accompany it. The problem with Utao was that code was not open source, so I could not look inside it to see how it actually worked. So instead, I found Cincy, a free open source vocal synthesizer, and decided to base my project off of it. When I looked into the code and documentation of Cincy, I found that there was a lot of math that I'll need to learn in order to fully understand what was going on. Cincy is a singing voice synthesizer that is based on the hidden Markov model and deep neural network. In order to understand what any of that actually meant, I had to take several courses online from MIT OpenCourseware. The first course that I looked into at the beginning of the school year was an introductory statistics course, taught by Professor John Ciziklitz.
How do we revise our beliefs? By calculating conditional probabilities. And how do we calculate conditional probabilities? We start from the definition of conditional probabilities. The probability of one event given another is the probability that both events occur divided by the probability of the conditioning event.
The reason I took statistics was to learn about hidden Markov models.
Given a system, how to properly define the state variables which will allow us to model its evolution as a Markov process is somewhat of an art, and there are no cookbook recipes to do it.
The second course I took was on matrix methods in data analysis, signal processing, and machine learning. This was taught by Professor Strang.
Is xk plus 1 is xk minus sk, the step size, times the gradient of f at xk. Okay. So the only thing left that requires us to input some decision making is the step size, the learning rate. We can take it as constant. If we take too big a learning rate, the thing will oscillate all over the place, and it's a disaster. If we take too small a learning rate, too small steps, what's the matter with that? Takes too long.
The reason I took this course was to learn about deep neural networks. As proof of my learning, here is a linear regression problem I've solved by hand, and also solved by creating a simulation using the gradient descent algorithm. By changing the slope and y-intercept of this graph on the right, the goal is to find the line of best fit. This means to find the line that minimizes the sum of squares of vertical distance between the line and the 4 points of this example. The graph on the left shows this visually, with the sum of squares of errors being the vertical axis. Finding the line of best fit for the graph on the right is the same as trying to find the lowest point for the graph on the left. The colored curvature on the left shows all values of the sum of squares of errors of the graph on the right, given a y-intercept and slope. The red dots represent the points that the graph on the right is taking to find the line of best fit.
This is the function f of x. F of x is going to be f3, let's say, of f2 of f1 of x. That's called composition. f1 of a vector would be, it includes the ReLU part, the nonlinear part, of A1 x0 plus B1. Now I haven't yet put into the picture the loss function. So that's the function that you want to minimize.
The loss function has the important job of distilling all aspects of the model down to a single number in such a way that improvements to that number signify a better model. With neural networks, we typically want to minimize the loss function.
The loss would be minus the true result from sample I.
After going through these two courses, it was time to go back to SYNC and vocal synthesis. However, the more I researched the topic, the more I realized its sheer depth. Vocal synthesis in general is based on speech synthesis, and SYNC was also based on other work. There were contributions from Cambridge University on the speech synthesis, Carnegie Mellon on text analysis, and Nagoya Institute of Technology used them for vocal applications. With the remaining time left in the year, I realized that I wouldn't be able to completely comprehend, let alone create my own version, of the collective work of several top universities over several decades. Instead, I decided to narrow down my topic and chose to focus on deep learning, since it has proven to be the most successful branch of AI in the recent past. I still wanted to create an AI that worked with music in some way, and with my understanding of deep learning that I obtained while researching vocal synthesis algorithms, I knew that deep learning was notably proficient with classification problems, like recognizing human faces or handwritten digits. So, I thought recognizing music keys with deep learning was also an interesting possibility. I found an introductory course to deep learning where I learned to use TensorFlow, an open source library that helps develop and train machine learning models. So, what actually is deep learning? Well, deep learning is a branch of artificial intelligence which focuses on the ability to learn patterns from data using neural networks. Simplified, deep learning is like a software simulation of the human brain. Typically, a single neuron is simulated with multiple branches for its inputs and a single branch for its output. As an analogy, you can think of each input to the neuron as a pipeline of water, and the weight values as valves, determining how much water from each pipeline is allowed to go through to the output. The allowed water from each input pipeline is added up before going through a gate that determines the minimum amount of water required before the water can be passed through the output. It is then possible to form a group of these neurons to make a neural network. There are multiple ways to form neural networks, but the simplest version forms neurons into layers, where information flows only in one direction. This is called a feed-forward neural network. Here is a simple feed-forward neural network with 8 inputs, 4 outputs, and totaling 5 layers. With multiple layers, the output of a neuron becomes the input of a neuron on the next layer. For example, the output of a neuron on the input layer becomes the input for a neuron in hidden layer 1, and the output of a neuron in hidden layer 1 becomes an input for a neuron in hidden layer 2, and so on and so forth. By adjusting the weights of the neural network, which you can think of as adjusting the valves of the pipelines, you can train the network to output desired target values given specific inputs. Depending on the size of the data, more layers or more neurons are required. Eventually, the end goal is to train the neural network to the point that it can take new unseen input and still give its correct output.
If there's only a few things that you get from this class, I really want everyone to take away how a perceptron works. And there's 3 steps, remember them always. The dot product, you take a dot product of your inputs and your weights. You add a bias, and you apply your nonlinearity. There's 3 steps. Let's simplify this diagram a little bit. Let's clean up some of the arrows and remove the bias. And we can actually see now that every line here has its own associated weight to it. And I'll remove the bias term, like I said, for simplicity. Note that Z here is the result of that dot product plus bias, before we apply the activation function, though, G. The final output, though, is simply Y, which is equal to the activation function of Z, which is our activation value. Now, if we want to define a multi-output neural network, we can simply add another perceptron to this picture. So instead of having 1 perceptron, now we have 2 perceptrons and 2 outputs. Each one is a normal perceptron, exactly like we saw before, taking its inputs from each of the x1s through xm's, taking the dot product, adding a bias, and that's it.
In order to make deep learning work, there are 3 big requirements. First, you need to have a lot of computing power. I ran my code on Google Colab, which meant that I could use Google servers to run my code. I also used the TensorFlow library in order to fully utilize the multi-core system of Google servers. Second, you need a very large set of training data to train the AI. One of the reasons this project seemed possible in the first place was because of the large database of songs and their respective music keys that are available for free online. I used SoundCloud to download songs from many large music labels and used TuneBat to find the keys of each respective song. However, since the data that I needed was going to be in the many thousands of songs and keys, it would be impossible for me to download each song and search up its key by hand. In order to obtain enough data, I had to automate each process. I programmed a simple web browser extension with JavaScript to automate downloading songs from SoundCloud. I also made use of an extension another person made that automatically scrolls down on any page. By combining my extension and the automatic scroller, I now had the ability to download all songs from a SoundCloud page. All I had to do was find a large music label from SoundCloud, use the automatic scroller to load all the songs in, then use my web browser extension to download each song as an MP3 file. I would turn on the automatic clicker, then come back an hour or so later with a large list of MP3 files. I repeated this process for several large music labels, with each label usually having several hundred songs to download from their SoundCloud. Okay, so this is a program I made with Python to find the key of each song by making queries to TuneBat. The tricky part here is that I had to extract the title and artist from each MP3 file name. So for example here, this is a block of code for filtering out the .mp3 from every title. Labels also often add extra text in file names, such as original mix, which I also have to get rid of. I also can't have the dash separating the artist and song title, since I found that TuneBat will not work if it is included. With this list of artist and song name pairs, I make a query to TuneBat, find the HTML elements that contain the artist name, track name, and the key of the song, and I double check those results to make sure they are valid before I save them. I also had to add a 10-second delay between queries, since TuneBat would have blocked me, deeming my automated queries as an attack on their server. And since it's so slow, I usually just let it run in the background during the day. And this is the result after several hours of running the program. The third requirement to succeed with deep learning is to have a smart algorithm. For example, a problem that arose was that the data size was now getting too large to upload onto GitHub, which I needed to do if I wanted to train my AI with Google Colab. I couldn't get rid of songs, so I had to find a way to reduce the file size of each song instead. With the downloaded music, I processed each MP3 file into a spectrogram, which is just a group of spectrums over time. I extract a small frequency range from each spectrum where the most melodic elements of a song are present. Each spectrum is 900 floating numbers from a 3-second clip of music. I extracted 40 spectrums from 40 different timestamps of each song. Each song was now only 144 kilobytes, which is 3% of the size of the average 5 megabyte typical MP3 file. I uploaded the files onto GitHub, organized by music key, and wrote a Python script on Google Colab to download it to use as a dataset for my neural network. Here is a quick run-through of the code for the neural network. First, I import TensorFlow as well as a few other libraries that I will need. Then I download the dataset from my GitHub to use for training. We can see here that the total number of examples that I now have is 4,658. And here is a print for the number of examples under each music key. Here are two examples of what a spectrogram for a song looks like, which I created to reduce the file size of each song. I now split my dataset into 3 parts, 80% into a training set, 10% into a validation set, and the remaining into a test set. The training set is training the weights of the neural network. This is done by calculating the gradient descent and changing the weight values a little bit at a time. The validation set is side-checking while training to see if the model would work in general with an unseen set of data. The test set is a final check after training is finished. Here I am creating my model. The main parts of it are the input layer, hidden layer with 1024 neurons, and the output layer with 24 neurons, representing each of the 24 music keys. The number of trainable weights now equal 947,224. Now I have to compile and start training the model. An epoch simply means the number of cycles the learning algorithm will work through the entire training dataset. As we train the AI more, the goal is to get the loss as small as possible and get the accuracy as high as possible. This process takes varying amounts of time depending on many factors, such as how many epochs I set, how many layers I add to my model, or how many neurons I put in each layer. You can see that as I train my model, the loss is decreasing while the accuracy is increasing. After an hour of training, we can check the results. This is a graphical representation of the model's accuracy increasing over time. You can see the rate of learning slowly decreasing the longer the model is training. With 300 epochs, the current test set accuracy is 77%, but there's something else we can also do. The neural network takes a spectrum as an input and gives the likelihood of each of the 24 music keys onto each of its output neurons. Since there are multiple spectrums made for every song, I collect the likelihoods of each spectrum and choose the music key with the highest occurrence for that song. By making a decision using multiple spectrums, I reduce the chance that the AI makes a mistake. Simply put, for every song, I'm rechecking my answer 40 times instead of just once. As you can see, using multiple spectrums before making the decision helps the accuracy a lot. This is the current state of my project. 86% means that if you give the AI any random song, it will be able to determine the right key 86% of the time. Now, I'm working on tuning my neural network by changing the number of layers, the number of neurons per layer, the training duration, as well as collecting more data. My goal is to eventually reach an accuracy of over 98%. Once I manage to reach this accuracy, I think the AI will have some practical usage to it, and I plan on making an app of some sort with it. At the beginning of the school year, the curricular competencies I was following were all from a Statistics 12 course. I think it should be fine for me to say that I went thoroughly over them. I spent well over 500 hours on this project over the year, with half that time on the mathematics to try to understand artificial intelligence at a deeper level. Thanks, that's all.